Hi everyone, good morning. Hope you're feeling good. Last day of the conference. Hope you had a nice time at the social yesterday. So you're in for a treat. I'm very, very excited for our next keynote speaker, Ellie Pavlick. Ellie is an associate professor of computer science, cognitive science, and linguistics at Brown University, and a research scientist at Google DeepMind. Dr. Pavlick leads the Language Understanding and Representation Lab, which seeks to understand how language works and to build computational models which can understand language the way that humans do. Ellie's work focuses on language broadly construed and often includes the study of capacities more general than language, including conceptual representations, reasoning, learning, and generalization. Dr. Pavlick's work has had a profound impact on the field and touches upon many domains of natural language processing, including work that provides a deeper understanding of the inner workings of large language models and what that means for language processing in humans and machines. Today, she brings us insight into one of cognitive science's most profound questions on how a system can achieve symbolic compositionality and how we can assess such behaviors in neural networks. So please join me in welcoming Professor Ellie Pavlick.
Thank you so much. It's great to be here. How's this volume? Is this okay? All right. If it's too quiet at some point, you can raise your hand in the back and I can turn it up. So I'm going to talk today about compositionality, which, as Laura was just saying, I think is a pretty central question. I like the question of compositionality because I think, like many topics we might think about, it kind of gets to the heart of some really core debates in the field, especially at the kind of interface between cognitive, neuro, and AI. When we think about compositionality, I think we all have a working kind of intuitive definition of what we mean by compositional. So the picture, like my go-to example when I'm talking to somebody like a non-expert about what compositionality is, it's the kind of thing that allows you to see a blue square and an orange circle and then generalize to a blue circle, right? And this is this idea that there's like these discrete parts, these colors and shapes, and they can be recombined to explain new inputs or stimuli or observations. This is always kind of the toy example. It's like nice, motivating, but then it's used as, or seen as really essential for more complex kinds of cognitive skills like language, syntax and semantics, and formal reasoning, formal domains like math and code, right? But then when we try to get more specific about an actual definition beyond specific examples, there's not a really clear consensus of what we're talking about with compositionality. So there are versions of definitions, I think of Barbara Partee, that just say like the meaning of the whole is a function of the meaning of the parts and the way that they are combined. She's talking about language in this context. And these kinds of definitions are useful for kind of providing that intuition, but they're not very useful for like differentiating computational systems or theories, right? Because almost any system we would posit would kind of meet this definition, and neural networks in particular would trivially meet this. You would say they're a function of their inputs, and so they're kind of compositional. And so instead, a lot of the debate has focused around more stringent definitions of compositionality, most famously like Fodor and Polishin, who have this idea that compositionality is about like an intrinsic connection between certain types of thoughts or ideas or concepts, because they're literally made from the same parts, right? So this is this idea that's embodied in traditional symbolic systems, the idea that like the thought of the cat on the mat and the mat on the cat are intrinsically connected because they are just physically built from the same representational units, right, in the mind. And so this is that definition. This latter one is the one that's really been, I think, at the core of a lot of debates at this intersection between cognitive and neuro and AI. Because this is one that's seen as maybe not compatible with neural networks, or there's been questions about whether this is compatible with neural networks. And so I think without taking a stance on what the right definition is, and I think most of what I want to talk about today is I don't think there is like one of these definitions is right or wrong, and sometimes the obsession of that might be misplaced versus focusing on more empirical trends. But I would say that the kind of my read on this definitional landscape is that there's a general agreement that there's something like compositional behavior. Humans have this ability to recombine parts or see, recombinations of parts in different holes and generalize this and have like very flexible power to generalize. But there's not much consensus about what exactly the thing is, how to define it, and in particular, like what kind of mechanisms might support it in humans, right? Like what kind of computational mechanisms, and particularly what kind of neural mechanisms might support this kind of an ability. So, of course, I will be talking about LLMs because what else is there to talk about these days? And I think LLMs are a really nice opportunity to revisit these questions because they're neural networks and they ostensibly produce compositional behavior. And there's so many examples of things that I think check this intuitive box of being compositional. So they do things like reasoning and inference. They're doing analogical reasoning. They're learning quickly. They're producing language. They're writing code. And so to the extent that we appealed to compositionality as like the thing that let humans do these things, well, LLMs are now doing these things, so they must be at least that amount compositional. And so this gives us this opportunity to say, let's shift the focus from having this kind of in-principle debate about what might be happening in humans based on these definitions, and just ask what are LLMs doing that allow them to achieve compositional types of behaviors, and maybe this can give us a window into what the kinds of mechanisms that might support it in humans. And so there's I don't have like a grand theory of compositionality, but I want to just focus on, I think, 3 emerging trends that we've seen in our empirical work in trying to ask these questions that start to form a kind of picture of an idea of what compositionality looks like in LLMs. And I'd say there's 3 kind of properties that have been interesting and consistent across results in our lab and similar studies in other labs happening at many different universities. So one is that the compositionality appears to be what we'll call structural, meaning that the network itself contains kind of reusable parts that are recombined. So the actual weights in the network specialize for kind of specific subtasks, and you can find reuse of these subtasks across different tasks. So I'll talk more about that. There's also a sense in which the compositionality is what we'll call functional. So when the model is solving complex tasks, it does this by breaking it up into subtasks, right? Which doesn't have to be the case in a neural network. We often talk about them as function approximators, meaning you could maybe estimate the value of some compositional function like f of g of h of x without actually computing h of x or g of x. But we find that that's not the case, that very often the models do compute the intermediate values. And these 2 types of properties I think are really interesting. For me, I would say a little bit perspective shifting as we saw this over the past couple of years, because these to me sound like the kinds of things that are reminiscent of like the photoimplicit definition and the kind of things we don't think of as neural networks having. And so there's this kind of version of saying, well, maybe what neural networks are doing is they are, merely implementing these symbolic systems of compositionality that we've known and loved or hated and resented for the past, 50 years. But then there's this third aspect that I think is really important, which is this kind of conventionality, context sensitivity to the compositionality that we see in neural networks that's not characteristic of those symbolic systems. So you can see that that they will sometimes but not always behave in this compositional way or have this compositional structure. And I think, digging into that third part and how it relates to the first 2 is the kind of exciting next frontier of figuring out how these things kind of integrate into this coherent theory of compositionality. So I'll go through each one of these in turn and kind of give some examples of the kinds of results which support these claims. Starting with structural. So when I think of structural compositionality, words like structure and function are just like so loaded. So I'll just say like the kind of motivation, what I'm thinking of with structural compositionality is this idea that of being made from the same parts, like the same physical parts. So I like this kind of example that comes up in language and language of thought a lot of like, if you say don't think about pink elephants, you just like can't not think about pink elephants. And this is because the thought pink elephants is just a literal part of the thought don't think about pink elephants, right? You can't instantiate the full thing without instantiating the part. And so this is, when I'm thinking about structural, it's like thinking about the actual architecture of the model, like the kind of literal physical stuff that the thoughts are made of. And so in this kind of when I'm thinking of structural in these results, we're thinking about like the literal weights of the network. And one thing that we've been finding is that these structured representations emerge in simple neural networks. So I can use a simple example. Here, this was a visual odd one out task, so that we have a neural network trained from scratch to identify an odd one out here, and in this case, it's supposed to identify the one on the right because it breaks on two features, right? It's neither inside nor in contact with the with one another. And so what we're going to do is we have our network, so we've trained it from scratch to do this odd one out task on these like little simple inputs. And then what we're interested in is finding whether there is a sub-network within the full network that computes the insideness feature, and then a separate one that computes the contact feature. And we're use some kind of pruning techniques to find these sub-networks. But what we're interested in, like if we say it's an insideness subnetwork, is we should see that if we use just this subnetwork to do the task, it should do a good job when the odd one out depends on insideness. But it should do a bad job when the odd one out depends on contact. And this is kind of a check that the subnetwork we found is not just a pruned down version of the whole network, but is like specific to the insideness feature. So visually, that'll just be points in this top left here. And then the opposite should happen if we ablate the subnetwork. So if I take out the insideness subnetwork and I use the remaining network to make the prediction, I should have the opposite behavior. And this is checking that the kind of insideness information is somewhat local to this subnetwork. So we tested across a couple different there's visual ones on the top and language ones on the bottom, a few different kinds of simple tasks and features. And you can see overwhelmingly the pattern holds where you see this kind of subnetwork specialization where you can find these networks and you can ablate them and they have the appropriate properties. I didn't include the random baseline just for space, but the one failure case I would say is panel F here, the top right. So if you have a randomly initialized subnetwork, you can always find something that computes the feature. But what doesn't happen in that case is when you ablate the feature, it doesn't really have an impact. So the information isn't really concentrated in a specific subnetwork. But after training, for the most part, you actually find this kind of concentration and localization that I would say is not was not my first instinct obvious that neural networks would do just from learning and data pressures. So I like this example because I think it illustrates the principle in this really toy network. The way that this kind of focus on structural compositionality, I would say, has been moving in the LLM world, has been looking at much more complex kind of interactions between weights and subsets of weights that are often referred to as circuits or mechanistic interpretability in the language model space. So there was some pretty good work, or pretty influential work from a lab at Berkeley, Wang et al. Several years ago, and they found this kind of circuit for solving simple language tasks. So here the task is Robert and Matthew had fun at school, Robert gave the ring to, and you have to predict Matthew here. And they found these attention heads, so those are kind of groups of weights within the language model architecture that performed specific functions in order to solve this task. So there was one group that basically identifies duplicates. It would say the name Robert is duplicated here. Then there was an inhibition component, which would basically inhibit future paying attention to the duplicated thing. And then finally, there was a copy or a moving component that would just copy names. And so what this algorithm basically looks like is say a name, don't say the duplicated one, right? It's a dumb way of solving this task. It's not like deep linguistic knowledge, but it works pretty well for this task. And this is something that emerged from not training on this test directly, but training generally on language modeling. So you see these kind of, the important from the compositionality point is that there's these kind of structural, these weights components that are doing things like finding duplicates, inhibiting, and moving that are specialized for those tasks. And so what we've looked at is whether these things are compositional. Are they task specific? Do they only work in the case of copying names, or do they do more general things? So we looked at some seemingly unrelated task. In this case, the model gets a question and answer, has to return the color of a object from a list. And we found that the model would use the same duplication component to identify the duplicated object in the question. It skipped this inhibition component, which I'll come back to later, and instead did a kind of promote attention to the duplicate component. And then it would use the same copy component to copy over the color. So you ended up with this kind of high amount of structural overlap between the weights and the kind of circuits being used to solve these two unrelated tasks. And then even more, like I mentioned, there's this kind of point of lack of overlap, right, where the inhibition component is not being used in the colored object task. And the model's actually really bad at the colored object task. It's actually at chance. It's guessing randomly between colors. And this might be because it's failing to use its inhibition component. And we found that if we actually just like kick up the activation of the inhibition component and say you should use this inhibition component to inhibit colors, then you can recover all of this accuracy. So there's this kind of, as a proof of concept, that these components exist in different tasks, but they can also be kind of rewired and they function as they should in the context of new tasks, right? I'll throw out that we found that these same kind of components reproduce across languages, including in models that are trained on entirely different data sets. So a model trained on entirely Chinese text will show the same circuits and the same components as one trained on English, which is, I think there's something very specific to the transformer about these are the kinds of things it likes to use to solve tasks. So the takeaway of this kind of structural piece being that the neural networks that I've learned to not say that transformers have no inductive biases. I think they have very strong inductive biases, and that can be like a question for discussion. But they don't have inductive biases for this particular type of structure. So we find this fairly minimalist, fairly generic architecture and training objective after training has this kind of fairly specialized architecture that manifests in the weights themselves, where you have identifiable regions that correspond to identifiable tasks and subtasks, and that they duplicate across different training settings and across different kinds of tasks that the models use at inference time. So I'll shift to something. I think that structural and functional are highly related, and I'm interested in thinking through that more, like in Q&A and just in future work, just like the extent to which one of these entails the other in the kind of neural networks we have, but they're not exactly the same thing. So we've talked about structure being the weights of the network itself, but then you can also think about compositionality kind of in the space of the task that the model is solving, right? So when we talk about functional, we're thinking about breaking up a compositional function into subtasks and solving those subtasks, whether or not you're using designated weights to do it. So this is very interesting. Like I said, I think a common criticism of neural networks in early discussions of compositionality, and even recently I've been on like panels for people who prefer more symbolic approaches to cognition, will use function approximation as kind of almost a dirty word, right? That the models can approximate complex cognitive tasks, but that doesn't mean they're actually performing the task, because you might just be like approximating the final output and not actually have learned the inherent structure of the task. So in this set, we're interested in whether models are kind of solving the subtasks on the way to solving the complex tasks as a way of approximating not just the final Y value, but actually the kind of path towards getting there. So here we're looking at simple kinds of factual recall tasks. So starting with just a basic task like finding the capital city of a country. So have some kind of A of X equals Y here. So like what's the capital city of Warsaw? And there's an analysis method that's common in large language models called logit-lens or various other kinds of tracing here, where you can basically look at the word that the model wants to produce at each layer in the network. And this is, I've thought of as something like a print statement for how the model is, I'm sorry to anthropomorphize thinking. We don't have the vocabulary otherwise, so I anthropomorphize freely, and apologies, but also kind of not. That's just how I talk. If asked, I will not say that they are thinking, like if I talk to a journalist or something, but among friends we can say. So you can kind of get a window into how the models are thinking about this problem as you move up the layers. And so you can see something like, what is the probability of the model that the model is assigning to Warsaw? And at early layers, there's no probability mass placed on Warsaw. It's actually just predicting kind of random tokens. I would say these are just like sampling from the prior of language, like parentheses, A, no, just like when in doubt, just say no. And there's actually, I think, a lot of interesting stuff to talk about in these early regions, but from this tool's perspective, nothing happening. And then you can see a short window about 2/3 of the way through the model where it starts to want to say Poland, and then it abruptly switches to saying Warsaw. And this is this kind of pattern we see where you see the argument to this function, the argument to the function surface first as the top prediction before the output of the function surfaces as the top prediction. And this pattern, so here the red line is showing basically the probability of Poland or whatever the argument is, and the blue line is the probability of Warsaw or whatever the output is. And you can see this general pattern where you get this crossing pattern that happens across models and across different types of tasks that have a similar functional form. And it's actually something that seems to get cleaner as models get bigger, this really nice kind of processing signature of giving the argument and then the output. So we've been looking recently in kind of ongoing work about whether this applies to more compositional functions as well. So you can say something like not the capital city of a country, but get the capital city of the country where a landmark is located, right? So A of X equals Z, you get some intermediate China, and then you're asking the capital city of China. And the question here is whether you get a similar processing signature, because you could imagine going straight from Yellow Mountains to Beijing to function approximation, or you might find evidence that there's an intermediate computation of China on the way to producing Beijing, right? And this would be a more, what we'll call a more compositional approach, where you're actually going to break this down into the sub-tasks. And what we find on aggregate, so we looked at a large number of tasks that have this kind of A of B of X functional form. And these include a lot of these factual recall tasks, but also some kind of math tasks and some string manipulations and things like that. And when you average over all of the cases, you can see that that very often, more often than not, there is this signature for that intermediate value, that yellow line peaks. So you get this blue, then yellow, then green kind of form in a fairly clean way. It's also interesting to say, again, on aggregate, but I'll come back to this, that this is true, that this signature is very strong when the model ultimately gets the answer correct. When it gets it incorrect, you don't see a significant signature for that intermediate value. But again, I'll come back to this because I think this is correlative, not really causal. There's also the degree to which, we're again related to this structural aspect, that like how modular are these functional representations. So we're looking at like this, basically at this crossing over point where these lines cross. This is associated with a particular place in the network where it is kind of applying the function, and that we can identify like the feed-forward networks that are active when it is applying this function. And what we can basically ask is it possible to port these over into new contexts and force the function to be applied? So what you can do is take some context, like what is the capital of Poland, and the model's going to say Warsaw, and then find the little piece of the feed-forward network where those lines cross and say, okay, the state of the network at this point, the hypothesis is this is a capital city function state. And so if I plop it into some neutral context where there's just like beep, boop, China, beep, boop, and it's going to say China again because LLMs are great at repeating sequences, but there's nothing here that really tells it should say Beijing. It should definitely say China. But if I splice in this, the activations at that point, we should force it to say Beijing. And this is kind of checking, is this really a functional representation? Is it look up the capital city of whatever you were going to say? Or is it a more idiomatic thing, in which case it might say like Warsaw? And we find in this specific example, very clean signature for getting the model to say Beijing as opposed to China, whereas before the intervention, it had absolutely no probability on Beijing. And on aggregate, again, across many different tasks, you can see that this pattern holds, right? So it's not always a perfect 100% intervention, but you very strongly boost the probability associated with applying this function after this intervention. So this suggests that this is quite a modular type of representation. So, kind of coming to this functional component, I think the takeaway here is that these subtasks, like when we have these complicated tasks, these f of g of h of x, the subtasks are represented somewhat explicitly within the model's processing, and they're often localizable and transferable. So you can find these activation space, and you can move it into a neutral context and get the expected effects. And we can at least find in some cases that they're chained together in these kind of multi-hop patterns to support more complex reasoning. So I think this is, again, this more kind of complicated picture than saying that the model is just like kind of merely approximating the output of this complex function. All right, great. So these first two, this, like I said, this structural and this functional, like to me, I would say it was when we started working on this kind of thing, this was really I would say surprising. Like I've now come to terms with this is how neural networks look, but like when we started doing this kind of interpretability work, say in like 2019, I was really of the mind that neural networks don't have this kind of structure. That's almost their power, right? It's like they're an alternative to this symbolic processing mechanism. So the fact that you find these representations both in the weights and in the way that's solving the tasks, and that it's kind of emergent as a consequence of training was kind of surprising and kind of changed my mental model of how they work. I also, in some ways, was like, maybe I just believe in symbolic systems. Like maybe they're just reinventing all of this stuff that was built into those systems, and maybe what we're going to see when we look under the hood is just this kind of mere implementation of these very symbolic architectures because of this kind of more modularity and more specialization and more compositionality than we would traditionally associate with neural networks. But I think that the most exciting part is if we can think about modern neural networks as providing both some kind of validation for these intuitions we have about this like structural and functional compositionality being part of an intelligent system, but also kind of an alternative to the traditional views of those. And I think that's where the kind of most potential for like theoretical insights would come from. And so what we've been looking at more increasingly is how models can kind of be of two minds and simultaneously do the kind of neural netty thing of being idiomatic and non-systematic in the ways that humans very often are, while also having this ability to recombine parts into new wholes in this kind of compositional way. So I'll call this kind of conventional compositionality just because it fit my, it sounded good with structural and functional, but it's kind of like context sensitivity, maybe. So I'll start by, I said I would come back to this example of these functional compositionality. So I had shown this kind of pattern where I said you can find this nice intermediate signature for this z value, and I said on aggregate this was true, and you can find really clean examples where it's just so beautiful. Like, so this task, the model has, it's basically take a word, take its antonym, translate it into another language like German. So an English word, its antonym in German. And here you can find a really, really clear signature for the antonym being represented in English, right? So the model really does first translate it to its antonym and then look up the German word. But there are other cases. On aggregate, this is what it looks like when it's correct, but there are cases where the model gets the answer correct and there's absolutely no signature of an intermediate value. So in this case, it's like take a number, add 100, multiply by 2, and it just seems to go directly from the number to plus 100 times 2. And this, it's a little more complicated because there's maybe multiple valid intermediate values, but we check for several different valid ways of computing the intermediate, and you can't pick up any of them. So it doesn't seem that in this case it's going through some intermediate function, at least in the kind of the set of things that come to mind when we think about these. So there's this kind of, like, yes, they sometimes have this compositional form, but not always. And so there's a question of like, well, why? Like, what determines whether or not the model will solve a task compositionally? And one thing we know about neural networks, and in particular their kind of input embedding spaces, is that they're extremely well structured, right? That even before large language models, we had word embedding models like Word2Vec. And one of the things that was really, these made these embedding spaces so famous was that they had this really rich relational structure. So like the country capital space in particular was one of the kind of favorite examples of supporting this kind of vector arithmetic, right? That there was a direction in embedding space that connected countries to their capital cities. And these spaces could be highly structured in more complex ways. So you might have like, primary dimensions in space that, for example, separate countries and their capitals, but then you could have like second order and third order and much higher order relations to pull out different subspaces with different geometries that would contain increasingly niche representational structure. And so our hypothesis was maybe that if you have this kind of rich structure in the input, whether or not models behave compositionally in their subsequent layers is dependent on this. So if it's possible to just pull the relation right out of the embedding space, there's no need to break it down into subtasks. You basically just pull it out. But if it's not easy to do it, or that's a nonlinear structure, right, then you would go through the compositional forms. And so what we would check here is basically if there's a correlation between how linearly the task is represented in the input embedding space and how compositionally the model solves the task throughout its layers. So by linearly, we're measuring this as basically how good is the linear projection from if I just take the embedding for the input X and then try to map it directly to Y without going through intermediates, I'm going to just train a linear regression and say how good is the fit for that. And when we talk about how compositionally is the task being solved, it's basically what is the maximum reciprocal rank of that yellow line, like how strong is the signal for that intermediate value. And we find a very strong negative correlation in this in the expected way. So basically, there's like points in this top left, things like the antonym translation task, where the model has a really strong signature for the intermediate value and a really low linearity, which basically means there's not a good direction in space that maps a English word to its German antonym, right? That's not something you can readily pull out of the input space, and so as a consequence, the model has to first translate it into English in order to then get the antonym. But other things, like for some reason, if you take a movie and you say what year was the director of the movie born, it doesn't seem that hard to actually get from a movie to the birth year of the director directly from the embedding space. And so the model never actually thinks about the director in order to pull this out. It just pulls it as a direct relation from movie to director's birth year. And so you have very high linearity, very low compositionality in this case. So I'm going to put this result side by side with seemingly unrelated results, and the connection being that I'll come back to, but I think there's this kind of interesting, more general trend where basically the extent to which it's compositional depends a lot on the kind of, I would call it like the rules and the structure that is available in the training data. So this case being, how I use a favorite word, I guess, like primitive is the relationship between the X and Y here. And if it's very primitive, you're not going to be compositional about it, right? So it's like that you have these rules and these features and these primitives that fall out of training data. You can use them directly, or you can compose them in more complicated ways. And we see similar kinds of patterns looking at a whole different set of tasks. So particularly like in humans, you can see this, what I would call this kind of context or condition dependent compositionality. So one set of results that we looked at here was this Decker et al. Paper from 2022. So here they were looking at how well humans perform on a compositional generalization task. And the task is you basically have a grid. You're placing colored animals along that grid, like where does the blue owl go? And they play with different curricula that you can give to the person. So you can say, you can show them all of the colors going down a column, and then all of one color, and then all of one animal going along a row. And this makes the kind of structure of the grid very apparent. It's easy to infer from this that color tells you the column, animal tells you the row, and then you would put the blue owl at position 1, and this shows good compositional generalization, right, in the very favorite shape plus color setting. But if you give people this interleaved curriculum, so if you just give them the same number of examples and you also cover all the rows and columns, but they're not in this really nicely structured format, then people perform much worse. They don't necessarily quickly infer the compositional structure of the task, and they'll be much more at chance to place the colored animal. And so this shows this kind of interesting pattern where it's like, yes, people are compositional, but if you change the nature of the task slightly and the training data slightly, then they are not. There's an older result, this Know et al. Task, that has a really similar flavor, not directly about compositionality, but thematically very similar with concept learning, where here they're showing us this concept learning task, so you have to differentiate between basically the blue group and the orange group. And they differ along these different dimensions, like the length and the angle of the line, right? And what they show in this paper is that when you give, when the kind of decision boundary is quite rule-based, so here in the left side here, you could basically, I like the phrase verbalizable rules. Like it's easy for me to say the short ones are blue and the long ones are orange, right? Like that's a easy for me to hold in my head rule. And so in this case, when you give the blocked curriculum, you show a ton of blue ones and then a ton of orange ones. People do a really good job at placing new stimuli. But if you pivot the decision boundary. So it seems computationally like it should be the same hardness of task, but in this case it's actually hard to just articulate what the difference is between blue and orange, because here you have, it's like, well, it's blue if it's short and not angled by too much, but if it's longer and angled by, right, then it's like harder to say. So in this case, if seeing a lot of blues and a lot of oranges actually harmed, it was harder for people to learn the category rather than shuffling blues and oranges. So in this case, you benefit from the interleave curriculum. So these, so I would say that these two tasks together present what can sometimes feel like this just like really noisy, complicated set of results where you're like, yes, people are compositional and they like rule-like structure, but only in some cases. If you change the task ever so slightly, if you change the training curriculum ever so slightly, their behavior changes a lot. This is, I mean, for this group, people are really comfortable being like, yeah, humans are really messy. I will say on the AI side, you would have a really heavy-hitting NeurIPS paper saying, like, look how irrational LLMs are. Look how sensitive they are to their input. They're clearly all, heuristics all the way down or something, right? So this is the kind of thing that would be very damning for an LLM, but, we humans do it all the time, right? But from a science perspective, it's like we now need some kind of coherent model that can explain all of this data, including these idiosyncrasies to these various task variations. So one thing that's really nice about modern neural networks, and one of the things that's really been associated with their increased power and abilities, is this idea of in-context learning. So we have this idea between learning in weights in the way we traditionally think of neural networks learning through repeat interaction with training examples, this kind of incremental updates to weights over time. You think about learning to ride a bike or something like that, versus what's now been called in-context learning. Some people like the word learning, others really hate it. I'm going to just use it because that's what people use in the field, which is learning in activation space. And so these are intimately connected processes. Oh no. Speaking of context sensitivity, this cord. Just unplug and replug.
I don't have anything profound to suggest.
Yeah, that wiggling is, I mean, it likes a very particular. There we go. Okay. All right. I'll touch very lightly. Yeah, so these weights and activations are not two systems, right? Like they are absolutely intertwined, but in a certain sense, you can think of them as kind of operating as two systems, right? And I think both that ability to kind of think of them as being different when they're actually very connected to each other is exactly why this is quite an elegant type of model. So obviously the weights produce the activations in whatever kind of as a function of context. And then this pattern of activations yields some kind of behavior, which is going to result in some reward or loss. And then once you get that reward or loss, you go back and update the weights. And over time, what happens is obviously you have certain types of patterns that can be figured out in activation space, right? These are things that are sufficiently consistent with what you've seen in training. This is why people, it's like, is there really learning happening here? Well, it's not retained at all, right? It's basically just you did the task. But in sometimes, and as you play with large language models today, like it often feels like you're teaching it a new task, right? Like these can be really complicated things that weren't directly seen in training. And yet it's kind of figuring it out in activation space, and this could be easier or harder to do. But once it gets it right, it's not going to go back and update its weights at all. And so you have this kind of duality where you have kind of the ability to do this slow incremental weight update, but also this ability to adapt to new contexts and solve new tasks in activation space, and then not retain what happened there and not make any weights updates. And so we have this kind of two-system flavor to it, where when the input data kind of, I like to think in terms of rules, it's like following the rules of training, then in-context learning dominates, right? Like if the thing you're seeing is consistent with the patterns of activation you're expecting to see, that you're trying to pull out, that you're trying to compose, then the model will solve it in activation space, and the properties of in-context learning dominate, which we'll talk about in a second, are the kinds of properties that tend to give you like compositionality and blocking advantage. And then when the task doesn't do that, then in-weights learning takes over, and the thing acts more like a neural network, acts idiomatic, and prefers interleaved examples, and doesn't generalize compositionally. So what we have is experiments based on like a meta-learned neural network that uses episodes of something like this colored animal task. So you have different grids, and you're placing animals along different grids. But it's meta-trained over many examples so that it's so that we can test its ability to like solve a new grid in context. And you can find the same kind of example that, or the same kind of pattern that we saw in the human data. So if you give it a new grid that kind of follows the rules, so animals are going to occur along rows and colors along columns, then you reproduce this blocking advantage that we see in humans. So it will much, much, much prefer to see the in-context curriculum make it very transparent that you get, that you see all of the animal and then all of a color, right? And actually, interestingly, it's like it really can't do it with the interleaved curriculum, right? So if you shuffle these up, it's just not used to pulling out the pattern in that way, and then it does a pretty bad job. And this is exactly what we saw in humans. When they see this kind of a thing, they prefer this blocking curriculum in order to generalize compositionally. But then this breaks when you rotate the task. So here we do similar to in that know-it-all paper. You just rotate the grid here. And what this is, all it's doing is making it so that the rules are not consistent with the kind of primitives rules that the model has learned to look for during training data. So it's learned that rows and columns are the right way to think about this grid. If you break the row and column structure, it suddenly gets thrown off. And actually, in-context learning fails entirely in this case because it's just not prepared to see it, right? So if you ask it to generalize to a new grid that's been rotated, complete garbage, just zero accuracy. But in this case, then you see the kind of traditional neural network thing take over. So then in-weights learning would take over, and it can learn to do this rotated thing if after repeat exposures, and in particular with interleaved curriculum, then it'll regain the ability to now think about the grid in this rotated case, right? But that it doesn't really like the blocking. If you do the blocking, you get this catastrophic forgetting that is characteristic of neural networks. So you can see this like more traditional neural netty kind of properties taking over here in this rotated case. So kind of coming back to what we talked about, this kind of conventionality, I think there's this really nice interplay between when we look at modern neural networks, they have this in-context ability and this in-weights ability, this in-context ability being the kind of thing that comes out of meta-learning that has like qualitatively very different properties than we typically associate with neural networks. But one thing that's so nice and elegant about this is that both systems still exist, right? So there are times when it makes sense for the in-weights learning to take over, and there's times when the in-context learning dominates. And in particular, we're seeing in-context learning and all of its nice properties like compositional generalization and few-shot learning and other kind of symbolic-y features. We see those things dominate exactly when the inputs are kind of consistent with the rules of training. Like the whole point of that system is to find rule-like structure in the world and impose this pattern recognition and rule-like structure on new inputs. But then when you get things that don't really obey those rules and they kind of are a little weird and idiomatic, the model can fall back and become more idiomatic and learn in weights, as neural networks often do. And so, and this happens fairly naturally without kind of like routing function that says, does this go to my in-context or my in-weights system, right? It just kind of happens naturally in the dynamics of these two systems that kind of co-emerge. Or they don't co-emerge, the in-context learning emerges from the in-weights. All right, so stepping back, I think kind of the more global point I like to make is like what is about compositionality specifically, but also just about the kind of role of AI right now and LLMs right now in our understanding of cognition and neuroscience. I think I would say uncontroversially, LLMs are our current like best non-human example of human-like behavior, right? We've never had a system that we can poke and prod like this that does so many things that really, like, sometimes you don't know if you're talking to an LLM. Sometimes you can't tell if something was produced by an LLM versus a human. And that's a really crazy world to be in and a very exciting world to be in. And so we get this, like, new opportunity to basically say, well, how does the LLM do the thing? And this just gives us new existence proofs of mechanisms that, at least in one case have supported this behavior. And this generates really nice novel hypotheses for how this might actually happen in humans. Of course, there are so many differences between LLMs and humans, and so it's not the final word, but it's a really exciting time to get to say, like, well, what might this look like in a system with different kinds of constraints? And there's a lot of excitement questions that come up if they're similar, if they nonetheless converge to a similar kind of mechanism, or if they have very different mechanisms. I think compositionality is a really good one to study because it's such a nice example of one of these long-standing debates that has been pretty marred in like philosophical and almost dogmatic kind of allegiances between like what kind of compositionality do you believe in. And so, but it kind of like shocked to the system to say, let's just make this an empirical question and let's look at a system that's not a human system and just say, well, how is it doing it? And the interesting thing that's happening when we look at LLMs is that you get this kind of middle ground that's not like the hand-wavy middle ground of like it's somewhere in between, but like kind of some specific principles of saying, look, here's certain predictions from one theoretical camp that have bared out and predictions from other theoretical camps that have bared out. So I'd say like one of the thing that I've just found really surprising and exciting is how structured and modular the representations are, right? Because this was something that has been strongly advocated by traditional symbolic architectures. It's like, look, if you want flexible, fast-learning, compositional, intelligent systems, you need structured modular representations. And a really early version of this debate, connectionism, would have said, no, you don't. And you kind of do, or at least there is we can't say directly, but there is definitely something worth reading into the fact that this has happened at exactly the same time that models have gotten so powerful, right? Like they're not succeeding with completely dense distributed representations all the way through. At the same time, oops. Oh no. Let's come and wait for it. Oh. That's right. I think just wiggling is the only. Okay. Can it last for one more bullet? I mean, I don't really need it for the last bullet. I can just say, there we go. Well, it's there. All right. It just needed the pressure off. It was like, okay. But yeah, so at the same time, it's not as though we could have replicated the kind of power of the current systems with, traditional symbolic architectures. And one of the things that we're seeing LLMs do very well, or very frustratingly, depending on whether you're trying to sell a product or trying to understand humans, is they remain idiomatic and highly context sensitive, right? So yes, you can get nice compositional fast learning properties, but if you change the prompt slightly, then you don't get it. Or if you change the learning slightly, then you don't get it. If you change the task slightly, then you don't get it. Again, really annoying when you're trying to provide a product that behaves consistently, but actually really nice when we're trying to explain something like human cognition, which is also very much that way, and we need a principled system that can be both ways. And I think LLMs have this like nice kind of organic way of mirroring that that simultaneously rational and irrational kind of nature of human behavior. All right, that's all I needed. Thanks. You can shut down. Thanks so much. I'm happy to ask questions.
Thank you so much, Ellie. That was amazing. So great. We have about 10 minutes for questions. We've got a couple of microphones. So great.
Hi, thanks. Great talk. I was wondering, so you gave this sort of historical introduction of sort of lenient versus strict. So where would you place your results? Especially the intermediate ones, with intermediate representations, like on the way to Warsaw, you pass through Poland and so forth.
Yeah, that's a great question. I could give a kind of two-part avoidant answer. So I would definitely say in the middle, as in like Well, I mean, maybe that those are more like a funnel or like a nested circles, right? The lenient one is very permissive. So any description of compositionality, I think it would be hard for it to not fall in the lenient definition. But I would say it's more, there's a lot of this constraints on what we're seeing that would say like, well, not everything explains this behavior. So there's this structural and functional stuff is like more stringent, right, for a kind of definition of compositionality. But I would, so I would say it's kind of a specific set of properties. I would put it somewhere in the middle. But the thing I was to say is avoidant is one thing I like about doing this kind of work is like, it's like descriptive, right, not prescriptive. So I'm not so interested in defining compositionality and saying this is what it means to be compositional. Instead, we're basically saying these are behaviors we're trying to explain. What is the mechanism that explains that behaviors? Then if people want to debate about whether that thing is compositional or not, like they can go crazy. I've now lost interest in it, right? So it's like you think of a lot of these definitions as being ways of trying to get us closer to a complete story, which I guess for me and probably many in the room, this is like, you know, an adequate computational description of the thing that explains the behavior. And so, yeah, at that point, like whether or not it's called compositional. And I have a similar like feeling about any other definitions that come up, like intelligence is a big one. Like, is this thing intelligent or is this thing reasoning? It's like, I don't actually care about whether it checks the box of yes or no, is it that thing? But I do want a description of the mechanism that explains the behavior that we're interested in. And so, yeah.
Hi, thank you very much for the great talk and really exciting new results. Compositionality is very often intertwined in the issue of the human singularity, and on many compositional tasks, human and children in particular seem to display compositional behavior in a way that non-human animals don't. Mm-hmm. I was wondering whether in your work you had elements to suggest why that could be. Is it in the architecture, in the whatever training regimes that could lead to this discrepancy between what we observe in humans versus non-human animals?
That's a super interesting question. Yeah, I think, so one thing that we have definitely didn't get into in the talk, and we haven't really gotten into in my lab yet, but we talk about all the time, would like to, is the question of like development, like where does this come from? But I do think, like speculating, there's a few, like I said, so the in-context learning system is emergent from the in-weights one, and at least in this last set of results, it's like the in-context learning system is really responsible for a lot of the compositional behavior, or the things we would call compositional behavior. That structural stuff and even a bit the functional stuff happens earlier, but I think wouldn't give us the full-blown compositional behavior that we would say is characteristic of human cognition. So I think you could tell a nice evolutionary story of these things building on each other and emerging, so that, yes, as you get more and more advanced cognition, you get more and more of these properties. And that would, I think, be consistent with this kind of a thing, where like you might find some properties of a compositional system in earlier things, but not the full-blown kind of, you know, natural language style of composition. I do think that there's going to be a lot of interesting work in the training dynamics and the learning dynamics and the scaling laws of these kinds of properties as we know more what we're looking for, and then we can track it over time. And I would hope to see something that provides something like an answer there. But I think the general answer is like emergence, right, where things emerge out of the others. So we probably would see things go along that continuum. But that's a really good, interesting next direction, yeah.
Yeah, thank you very much for the very interesting talk. I guess I have a bit of a follow-up question for the last one. I think even though we humans also fail at compositional generalization at times, I think there are many interesting modes where we humans don't, which are kind of like trivial cases where the models do fail. And I'm wondering if it has something to do with the in-context and in-weights learning, where like, well, you said something very interesting in your second part of the talk, where you think that the symbolic representations might emerge from purely the neural representation, but I think there are other people who claim like, well, we need to explicitly still incorporate symbolic representations, like this whole neurosymbolic AI field, I guess. What's your stance on that? I'd be curious.
Yeah, that's, a few questions in there. So like one is kind of where the analogy breaks, or even the similarity breaks between the humans and machines. So yeah, there are many examples of compositional generalization failures in LLMs that are not human-like, right? But one thing that is, like, I've been thinking more about similarities of principles and mechanisms that explain the behavior than similarities of behavior per se, because there's so many differences between the data that people got. So my go-to answer for this, which could be wrong, but my current thinking would be like, well, both humans and LLMs are breaking on compositional generalization when the input like violates some kind of set of rules according to which they compose, or some other cognitive process intervenes, right? Which both of these are kind of good things that we say for humans, like for proponents of that humans are more rational kinds of beings, but then often behave irrationally. It's like, well, there's a lot of other pressures that can come into place in other heuristic reasoning processes. And I think that that explanation is a good explanation for LMs too. It's just the types of heuristics that they're using are different ones that emerge from different things, but they also might have this ability of like kind of knowing the right answer, but choosing the heuristic answer because they misunderstand the objective or something, or they're, different considerations way out. So I'd say like on a abstract kind of mechanisms and principles level, you could have a lot of similarity, but on an actual behavior differences just because the exact data and the exact training objective is different. So I think there's a lot of work to do to bring these things closer into alignment so we can get more specific about the predictions and where they pull apart. On the neurosymbolic stuff, this is one where I have a hotter take, where I'm generally of the feeling of like, nah, it's not necessary. I'm moving. So I would say like when I started out of PhD, I was like, it's absolutely necessary. Humans have all of this kind of complex capabilities, and if we want to replicate human-like processes, systems are going to need to have them. Systems are going to need to have them, and so we're going to have to build them in. Then from all of this kind of work, I've been surprised at how much it emerges, like symbolic-like stuff emerges. So it's not that I think they're not necessary, but it's that maybe I'm increasingly feeling like the burden of proof is on showing that the thing you build in is superior to the thing that would have emerged with the right conditions, because I actually think in many ways like the thing that emerges is similar to but not exactly the same as the thing that was built in. But I also, like, I expect to move back the other direction just after enough time. The pendulum swings back and forth. So there are a lot of good counterexamples already that I would cite to argue against myself. One being, if not built into the architecture, built into the training, there's pretty significant symbolic feedback in current systems, including training on language, which is extremely symbolic in nature, training on code, executing code, and training through RL on that. So there's like the symbolic bias is very, very strong in the objectives and the data. And then also, like I said, I think like transformer architectures have like the attention mechanism they use looks a whole lot like the kinds of things that people who talked about neural Turing machines and distributed memory would have built in before. So like there's, this is not one giant multi-layer perceptron, right? Like it is a really intricate architecture. So that's a pretty big win for people that are like, look, you need to build in some biases for these things to work. And the truth is when you look at other kinds of models, they don't necessarily have the same behavior, right? So we don't have a lot of other things to compare against, but like vision models, which use diffusion models, don't necessarily have this in-context learning abilities and stuff like that. So yeah, so I think there's still plenty of room for me to say neurosymbolic is dead. Like I expect to just be very wrong and to eat those words within a couple of years.
Yeah, thank you for the great talk. This is fascinating. I'm curious how you see this line of research sort of integrating or contributing to sort of the broader suite of mechanistic interpretability stuff that's going on in AI. Have you thought about utilizing some of the more contemporary and popular techniques like sparse autoencoders and other things in that realm to sort of add extra context to this research?
Yeah, yeah, we definitely use, every time a new technique drops, everyone in my lab jumps on it for a second, and we're like, what can we do with this? I think I'm of mixed minds on mechanistic interpretability. So that's for, if people aren't super on top of that word, that's kind of the word that is assigned with like finding these circuits within large language models. And it's usually used more of like people who are trying to understand LLMs for the sake of understanding LLMs, often from like safety research perspective, but has a lot of nice connections to cognitive neuroscience because of the focus on like mechanisms. Yeah, it's gotten really trendy, annoyingly, and so there's a lot of rush to produce new methods. To me, I usually take a slightly deferred uptake of them because they need to be like substantially different. And like it's still, we try to mostly be hypothesis driven in the research. So it's like, what's the best tool to answer the question? So for things like sparse autoencoders and a lot of these things, I just haven't found them that deep for the types of things we're interested in. I think there's a huge gap and need for new methods that just don't even begin to, that none of the new things begin to touch on. So for example, all of these methods really presuppose that the model is thinking in language. So you have to be able to express your thoughts in token space and construct inputs in this way and read out the meaning of a neuron or whatever in natural language. It's a huge assumption, and a lot of really interesting structures will not fall out of this. A really good one that resonates is stuff like variable binding. Like the model is not going to say, this is the variable binding neuron. It'll say, something weird in natural language that you would, as the researcher, would need to have that hypothesis to infer that that's what's happening. So in kind of true AI, Silicon Valley fashion, there's a big focus on automating the work, and I think it's too soon to automate the discovery. I think there's still a lot of need for like hypothesis testing, intuition about what's an interesting thing to look for. And then given that there's a lot of methods, so it's great that there's so many methods, you can look through and use the best one. There's also a lot of questions that the methods don't allow us to answer yet, so I think there's still a need for new methods.
Hi, thank you so much for the talk. I had a burning question that came up in the middle that I wanted to ask you about, which is something like a lot of the data you presented it's completely new to me, find it fascinating, but I was wondering at some point how much of it is a correlate of composition rather than an actual demonstration of composition happening. And I think one particular point where you showed the plus 100 times 2 case, that it was a failure there. I started, and then you were later showing the word-to-vec kind of transformation between different types of tokens or so, had me wondering like how much of what we're seeing is actually a correlate of composition that is something like the representational space is set up in a way where, for example, man and king have a certain kind of relationship in the same way that queen and woman do. And how would we tell the difference? And where are you thinking about how we can actually determine, like, is this composition or is this a correlate of composition that's encoded in the data structure or representational geometry? Yeah,
this is a great question. So I have probably a couple pieces of answer. I think this, I guess one to point to this previous question is I think this, looking for the intermediate value is a really good example of where the methods matter a lot. So we very much have this suspicion that a lot of the cases, the model might actually be computing the intermediate value, just not in language space in a way that's readily detectable. So it could be that the model has a representation, however defined, that's a loaded word, but a representation of x plus 100, say, but it is not the token corresponding to that number, because language space in the model has a really important role to play in representing inputs and outputs, and it does not have to be the way it represents internal thoughts, right? So there's a big open question there about what if the model is representing a thing that is non-language space, and this is where our current tools, were defined by people interested in LLMs, not interested in other things, and so therefore they just take for granted this. Okay, so I think there are a lot of questions like that, and this is one thing that I've been spending a lot of time just thinking about. Is like, how are we going to find these other representations? So I think that's an important piece of answering these questions. But then this question of like, is this a correlate of compositionality versus a actual compositionality happening? I think so there's a two-part answer. So one is we want to say like when we find a piece of representation that looks compositional, it's like, is that thing kind of causal in the output? So there's a lot of work on causal interventions. I showed some of them on things like splicing in the representation of the function, and you can do other kinds of things. So we've been starting to work on some causal interventions to say, like, if I can get the model to compute a different intermediate function, does it change the output? That would be compelling evidence that this representing that intermediate value is causally implicated in the other. This is a longer discussion, but I also am like, about a lot of the methods for causal intervention, because to me they're circular in a way that's frustrating, and so it's like it'd be great to have those results, but it wouldn't close the book on it for me. But then there's a second question, which is kind of like this question of definitions, like, is this a correlative compositional behavior versus actual compositional behavior? And then this requires some definition of, like, what is the God-given actual compositional behavior? And then my answer is I kind of don't care. So, like, if I have a good descriptive model of the mechanism and saying this is the thing you need to do, these are the inputs and outputs, these are the mechanisms by which they are combined, this perfectly explains human behavior or whatever behavior on the task, that's the thing. Is this a correlative compositional? Is it actual compositional? If the work is done as in we've like answered all the questions that are to answer, then I don't care what it's called. Of course, there will always be questions of like, where did it come from? Why did it emerge and stuff? And so we can, but I like this kind of pivot onto like, what is the mechanism, what's happening, and how does it explain behavior? And I think if we focus there, then it prevents this kind of, navel gazing around some of the words. Yeah, so that was a many part, also kind of avoidant answer, but thanks for the question.
Thank you so much. So let's give Dr. Pavlick another round of applause. Thank you.